Good morning, students. Good morning, students.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning,
How
sir.
are you? How are you? So
Fine, sir.
we start the class in the next 2 minutes. Sorry. So we start the class in the next 2 minutes. And before that, let me make some people co-host so that nobody will disturb the class. And if anybody is disturbing, we can meet the person. Okay. Amen.
Let's go for it.
Who's professor? Who is this professor? Why did you use your name? I just saw professor. Who is that person? The Yaya Abuba. Is he Abubakri or what? Let me make you a co-host. Yaya Abubakri. Yeah, a co-host. So you can mute anybody making noise. Adeyemi too. Adeyemi, let me make you a co-host. Adeyemi Uzin. You are not a co-host. You can mute anybody disturbing the class. Let me use the Google Base too. Ogunjobi Khadija. So you are not a co-host. So you have the power to mute anybody that is making noise in the class. So where are your people? Are people not joining the class? We are around the 1,000 now. I just saw 60 something now. So I want to, I'm already streaming on YouTube. So I will copy the link to the Telegram group. If anybody cannot join the Zoom, he or she can go through the YouTube. He or she will still enjoy everything the students and the Zoom are enjoying. So let me copy the YouTube link. Okay, the YouTube link is already on our Telegram group. So anybody that wants to join can join through the YouTube. So we can start the class now.
I'm in Zoom. I cannot ask you a question. Which one don't disturb me? Come and beat me then. Come and beat me. Any small thing you get in being with somebody. Did I ask you what did I ask them?
Our co-host should do the needful. Some people are disturbing the class. I expect you to meet the person.
Stop listening at me. I'm not your mate.
Okay. So I want to welcome you students to this class once again. C-PHY 103, General Physics 3, behavior of matter. So last week we were discussing thermal expansion of solid and liquid before we round up the class. So we start from there, from where we stopped last week. So, and I want you to pay attention so that you can understand what I'll be saying. Thermal expansion of solid and liquid. So I told us that if temperature of a solid increases, its dimension also will increase. That is, you have a solid and you increase the temperature of that solid, it length or the area or the volume of that solid can increase. For liquid, if you increase the temperature of a liquid, its volume also can increase. So as we know that we cannot say this is the length of a liquid or this is breadth, but its volume will increase. So an exception to this is water. I explained that last week. Exception to this is water. Why do we say exception to this is water? Because when you increase the temperature of water from like minus, let's say -5, -4, increase temperature, the water will be expanding. You know, at that point, it will be ice. So it will be expanding. So when the temperature gets to 0, and you are still increasing the temperature, from 0 until temperature becomes 4 degrees, water will be contracting. You know, this is strange. It's very strange. So you are increasing the temperature when the temperature was like minus something. You are increasing the temperature, and you see that it begins to expand until temperature increases to 0. Then from 0, you are still adding the heat. You are still supply energy. You see that water begin to contract instead of expanding. So until it gets to 4 degrees Celsius. When it now gets to 4 degrees Celsius, it's now begin to expand normally like any other liquid. And this is what is called an anomalous expansion of water that they used to ask you in WIAC that explain the anomalous expansion of water. This is what you will tell them. This is what I used to tell them if you have answered any question like this before. That below 0, when you increase the temperature of water, it will expand like any other liquid. When it gets to 0, it will be contracting until the temperature gets to 4 degrees Celsius. Then after 4 degrees Celsius, the water begins to expand. That's why they will tell you that water has the highest density at 4 degrees Celsius. So, and this is anomalous, or anomalous means unusual, something that is not conventional, something that's not usual. You can call it unusual behavior of water and expansion. So anomalous expansion of water. We have said that last week. So, and if you are not around last week, it's an opportunity for you to understand what we said last week. So this phenomenon that I've explained is what's called thermal expansion. That is expansion that is brought about by the application of heat. Thermal means heat. So expansion that's brought about by the application of heat is called a thermal expansion, both in liquid and solid. So they are called a thermal expansion, and it has many applications. So I told us application areas in which we can thermal expansion can be applicable. So like probably when they are building railroad tracks and they are laying rods, you see them, they are laying a metallic rod. We see that they will leave a gap between two rods or two rays when they are constructing bridge too. So when they are constructing bridge and they are laying their pipe, they are laying their rails, they are laying their rods, they always leave for gaps in between the rails, in between the rods, so that expansion can be allowed when temperature increases. So, and I believe many of us are familiar with this thing right from our secondary school. So, and I explain what's it called, expansion. How do we come about expansion of a solid? I told us that the atoms of any solid are vibrating between their main position. They are vibrating between their main position. Then, but when you supply energy, when you increase the temperature, the vibration amplitude increases. That is, the distance between them becomes increasing and increasing. They begin to oscillate in higher amplitude. So little by little, you are still supplying. You get the point that you see that the distance between these two atoms has increased more than their normal distance, which is 10 raised to power minus 10 meter. So then you will see that expansion has taken place. So that expansion has taken place. Yeah, I say as temperature increases, the amplitude of the oscillation increases. And as a result, the average separation between atoms increases. Consequently, we say the object expands. We say the object expands. Sorry, there should not be S in one of them. So, and I said, note, the ratio of the change in the length of the original length, ratio of the change in length, this change in length is just a single letter or a parameter, to the original length, to the degree rise in temperature is called the coefficient of linear expansion, or the way you call it before, linear expansivity, and is denoted as alpha, this symbol, alpha. So the ratio of the change in the length to the original length to the degree rise in temperature is called the coefficient of linear expansion. So, or they can still call it linear expansivity, and is generally denoted by alpha, except if otherwise stated. So it's always alpha, but they can use another symbol. Don't just say it's alpha, but generally it's denoted by this alpha. I said if thermal expansion is sufficiently small relative to the initial dimension of the object, then change in length over original length is always proportional to temperature change. And I told you, look at the condition above, that if the thermal expansion is sufficiently small, that is, if it does not supply great heat that can break the bond between the two atoms. Because if you supply great heat, that's more than the energy to break the bond, then this proportionality will not take place again. So change in length over original length will not be proportional to temperature change. So, and I think I explained this one last week. I explained very well. So then I say delta T, which is this one, is temperature change. Delta L is change in length, while L high is the initial length, or you call it original length. So from here, from this line, I can have delta L over Li is equal to alpha delta T. You know the reason, you know why I did not put a proportionalized symbol? I use an English symbol instead of using that proportionalized symbol. You know, proportionalized symbol is like our coefficient of linear expansion. So if I put it there, you will think it's linear expansivity I put there. That's why I say delta L over Li is proportional. Instead of putting that symbol, I just use English so that I don't miss the symbol. Then, you know, in mathematics, in variation, they will say you will remove the proportionalized symbol and you put equal sign and a constant. That's what I've done here. So this is delta L over Li equals, I remove the proportionality symbol. I put equality symbol, then a constant multiplied by what we have at the right-hand side. So that if I cross multiply, I have delta L, that is change in length, equals alpha Li delta T. If you have gone to a good secondary school, this is just elementary physics. You are supposed to have done SS1, but I didn't miss it. So alpha is the coefficient of linear expansion with the constant in the equation. Then this implies that change in length, that is LF is the original, the final length. After you have increased the temperature, the length that the object increased to, minus the initial length or the original length equals this. I just write this equation like this because the L is the change in the two lengths. The delta T is not the change in the original, the two temperatures. This Ti is the initial temperature, while Tf is temperature to which you increase it to. Then from here, I can write my alpha like this, which is the coefficient of linear expansion to be this. Just make this alpha the subject of formula. You have this thing. So this should be Li, Lf minus Li. So this gives the definition of the coefficient of linear expansion. This is where they derive the definition from that I gave you before. If you remember, I say the ratio means division. The ratio of the change in the length to the original length to the degree rise in temperature, that is to the change in temperature. This is the definition. So that's why in physics, they will tell you in secondary that if you don't know the definition of something and you know the formula, you can write the formula, but you need to define each term. You need to define each term so that they know what you have defined. So alpha equals delta L over Li multiplied by change in temperature. This is actually the definition. If you look at what I gave you before, look at this note. The ratio, that's the division of the change in length, delta L, to the original length divided by Li to the degree rise, that is times temperature change. So that is that.
My pod inside. My pod.
The co-hosts, what are you doing? You cannot allow people disturbing the class and be looking at them. So, okay, let's continue the class. Thank you. As this is all the, okay. Okay, since all the linear dimensions, that is length, breadth, and height of an object change when the temperature change, it implies the surface area and volume also will change as well. So I've said that before, that for a solid, when you increase the temperature, the length, the breadth, and the height also will increase. So the ratio of the change in the area, when you increase the temperature of that solid, the length will increase, the breadth also will increase, and the height. That means the area also has increased, and the volume also. So then I can write this, that the ratio of the change in the area to the original area, that's like a delta A over AI, then to the degree rise in temperature, that's multiplied by change in temperature. It's called the coefficient of area expansion, which we call a superficial expansivity. And it's denoted by, sorry, I have to put that, it's denoted by beta, something like a B. Oh, this is it. This is superficial beta. So, sorry. Similar to change in the length, we still have change in volume over original volume is also proportional to delta T. So also the area. The area can be delta A over AI, that's initial area, is proportional to delta T. All these three are related. It's only the dimensions that are different. If you know one, you can remember the others. Then from here, I have this. That is, I remove the proportionality symbol, I put equality sign, then a constant. This constant here now is volume, coefficient of volume expansion. So coefficient of volume expansion. So if I cross multiply like I've done before, I will have delta V equals gamma VI delta T. This is exactly like the length when we are dealing with linear expansion. Like we have delta L equals to alpha Li delta T. But instead of L, we'll be using V for volume. So delta V equals gamma, that's coefficient of volume expansion, multiplied by the original volume times change in temperature. So, and I told you delta V, that's change in volume, original volume minus initial volume, multiply delta, gamma is this, then original volume is still this, then delta T is TF minus TI, where gamma is the coefficient of volume expansion and is defined as this. This is where they see the definition. So I've said before. So if I want to define this now, I can say coefficient of volume expansion is the ratio of the change in volume to the original volume to the degree rise in temperature. That is delta V divided by VI multiplied by temperature change. So as simple as that. All these things are simple. If you have listened well before, they are very simple. But many of you will be saying, when I enter in first year, I will not do physics, I will not do physics. But now you are doing physics. You didn't pay attention to your physics teacher. So if you listen well, this is another chance for you to really understand. Okay, I've said that similar for the area. If I cross multiply, if I have delta A over AI multiply, I change the temperature and I cross multiply, I will still have the same thing as I have before. This is delta A for change in area multiplied by, is equal to multiply by, what's it called? Superficial expansivity multiplied by original area times change in temperature. Let's compare this equation with the previous two. Let's compare this equation with the previous two equations that are something that we have. We see that here is exactly the same thing as that one. It's only the dimension are not the same. This is volume, and this is coefficient of volume expansion. So look here too. This area, this coefficient of area expansion. If you check the area, the length also is still the same thing. So please master that. For those of you that have not known that before. So I said beta is the coefficient of area expansion. So record this. This is very important for you to note. For any solid, gamma is always 3 multiplied by alpha. That is, coefficient of volume expansion is always 3 multiplied by coefficient of linear expansion. It is very important you know this, because many times they will give you a question. They will not give you volume expansivity. What they give you is linear. You have to know the relationship between them. And also, beta is equal to 2 multiplied by alpha. That is, coefficient of area expansion is always 2 multiplied by coefficient of linear expansion. So from here, listen well, from here you can relate the beta and gamma too. Try and relate that. So if you have gamma is equal to 3 alpha and beta is equal to 2 alpha, you should be able to relate gamma and beta. So let me give you a clue. You can just make alpha the subject in one of them. Let me make alpha the subject here. My alpha will be beta over 2. I'll just put it here. That means gamma will be what? 3 beta over 2. So very important. So for this, we can prove how this becomes this. We can prove how gamma becomes 3 alpha and how beta becomes 2 alpha. So to show that, consider the box below at a temperature Ti. Let's say the initial temperature is Ti. So this is the box. I have the length of the box to be L. I have the breadth to be width. I call it width, breadth, yeah. Then D to be the depth or the height. We want to show that gamma is equal to 3 alpha. So initial volume is Vi. I means initial, to just differentiate between initial and final, and Ti is the initial temperature. So if I increase the temperature now to another temperature, I can call the final temperature to be what? Ti plus that increase in temperature that I added. So volume also will be the original volume plus the change in volume. I've told you, go and listen to the what's it called? To the YouTube link. That's why I copied the YouTube link to the Telegram group. After the class, you can go there again, listen to it often, or you can download it. Instead of sending a request for recording, you are like 400 plus. So how many people will I be answering? So go to the YouTube, download it, or listen to it on YouTube again and again. So I said that the initial temperature is Ti. the initial volume is VI. When I increase the temperature of this box, the length will increase, the width also will increase, and the height. So that means after I've increased the temperature to a particular temperature that I don't know, I can say the final temperature is Ti, that is the initial temperature plus that change in temperature that I added. Its volume also will be VI, that's original original volume, plus delta V, that's change in volume that I added as a result of change of its dimension. So therefore, initial volume is what? Length times breadth times height. We all know that. So, but here I've used W to mean the width and D to mean the depth. It's still the same thing as length and height. So this is the formula to calculate the initial volume of the box. Then after I've increased the temperature, the final volume will be what? That's a final length multiplied by final width multiplied by final depth. But I've told us the final length will be initial length plus delta L. Final width will be initial width plus delta W, and final depth will be initial depth plus delta D. If the coefficient of linear expansion is the same in the three directions, then we have this that I've told you before in the three equations. If you remember the three equations I compared, I have delta L is equal to alpha L I. That's it. Hello. Hey, Jack, please. I'm in class. Okay. Huh? Okay, I'm taking 100 class. Please, you can come back. Sorry, students. I need to pick that up. So, final volume will now be this one inside the first bracket is the final length. This bracket at the middle is the final width. And this last one is the final depth. So if the coefficient of linear expansion is the same in the three directions, then we have this. That is, I've showed you before that delta L is equal to alpha Li delta T. For W, it should be this also. Alpha, because three of them are like length now. So we use linear expansivity. We use coefficient of linear expansion for them. You know, breadth is also like length, something like a straight. Then depth also is still the same. That's why I used the what's it called? Coefficient of linear expansion. So instead of delta L, delta W, delta D, you can put these values there. You can put this there. Here, I'll just pick this here. I'll put it here. Then this one, I'll put it here. Why this one, I'll put it here. So if I do that, I will have this equation that I have. And I believe you understand that it's a very simple mathematics, just like a substitution. So if you look at this equation, you will see that here Li is common, here Wi is common, here Di is common, and they are multiplying each other. Each bracket is multiplying. We can factorize Li, Wi, Di out, as I've showed here. Yeah. So when you factorize it out, you have 1 plus alpha delta T. Let's go back to that equation so that we understand better. If you factorize Li out, this will remain 1. This will remain alpha delta T. You factorize W, this will remain 1 alpha delta T. Factorize Di out, this will be 1 alpha delta T. You see that you have 1 plus alpha delta T that is common to 3 of them. So I have 1 plus alpha delta T, 1 plus alpha delta T, and the third one, this is Li, Wi, Di. If you look at this, this looks like our initial volume. This is our initial volume, exactly. That is the initial length multiplied by the initial width multiplied by initial depth. So I can write this one like this because I have 1 plus alpha delta T in 3 places. I can write it as raised to power 3. So, and you did the expansion. That is, if they give me a plus b raised to power 2, I can write it in 2 ways and expand normally. But if it's more than 2, like 3, you can still do 3. But if it's more than 3, you can use a binomial expansion, or you can still use a Pascal triangle to do that. So anyone you know, what I did is that I just expanded this 1 plus alpha delta t raised to power 3. So if I expand that well, I will have 1 plus 3 alpha delta t plus 3 alpha delta t squared plus alpha delta t raised to power 3. So you can lay your hand on this. Expansion is what you have done right from elementary level in secondary school. 100 level, what's it called? GS1, GS2, you can do expansion. So lay your hand, you will see that you arrive at this one side is square bracket. So, and you know that our delta V is equal to final volume minus initial volume. Final volume is what we arrive at now, this long equation. So that's what I put here. Minus initial volume. You remember the initial volume, this initial volume that I told you that we know. Then if you look at the two sides, on this side I have LIWIDI. On this side too, I also have the same thing. So I can factorize that out. If I factorize LIWI out, I will have factorize out, this one will be 1 plus 3 alpha delta t plus 3 alpha delta t plus this, then minus 1. You know, you have factorized this one. This one will be minus 1 will be here. So which will be the next line. Then because I have plus 1 here, this minus 1 and this plus 1 and this minus 1 will cancel. That's why I have just what I have inside the square bracket. Some of you might have been saying, where is this one? Where is this? You know, that's what I did. I factorized LIWIDI out. And here, you know, if I bring out this one, it will be minus 1. So that minus 1 will now cancel this 1. So you now have what you have inside this square bracket. So this is my VI, that is initial volume. If I divide it by both sides by initial volume, I will have a delta V over VI equals 3 alpha, everything inside the square bracket. And I believe you understand this. Well, you can still ask your question later after the class. So I divide both sides by VI. So I have delta V over VI equals everything inside the bracket. It's like I brought this one under this one. It's around me, this one inside the square bracket. But you know, coefficient of linear expansion is always a small value, like 0.0001. Most time, like 10 to the power minus 6 value. So if you have a small value and you square it, you get a very, very small value. If you raise it to power 3 or raise to any power, which is not a negative power, you get a very small value, a very minute value that you can neglect. So that's why if I apply that, this value will be very small because this is a coefficient of linear expansion. I've squared it here. It is squared here. So this value will be very, very small. Look at this one too. This value will be very, 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 and very small. So I can neglect them. So that's what I've done. I said since alpha is usually very small, then this value, alpha delta t raised to power 2 and alpha delta t raised to power 3 will be small compared to the first term of the alpha delta t. Therefore, they can be neglected. I've said that before. So in that equation, it will just remain delta v over vi equals 3 alpha delta t because I've neglected the other two. So this is value. Then from here, I can represent 3 alpha, this 3 alpha with gamma. So that's where they see delta V over VI equals gamma delta T. So that's where they see that gamma is equal to 3 alpha. So this is what they did before they know gamma is always 3 multiplied by alpha. So as you can see, and I believe the way I've explained, you should be able to prove it also. So from here, I can have this, which we have as the change in volume equals gamma VI delta T. So as simple as that. So assignment that I will give you is that in a similar manner, it can be shown that for a rectangular plate, instead of a box, for a rectangular plate, the change in the area is A equals 2 alpha, this should be delta A, not A. It should be delta A equals 2 alpha AI delta T, where beta equals 2 alpha. You need to prove this. You need to show that beta is equal to 2 alpha. That's the assignment that you have to do and submit. So let's quickly look at these following examples, solved problems. I say a segment of steel road track has a length of 30.00 meter when the temperature, I cannot say that, sorry. Okay, when the temperature is 0 degrees Celsius. Yeah, when the temperature is 0 degrees Celsius. What is its length when the temperature is 40.0 degrees Celsius? We should be able to do this, and if no, I can still quickly explain that. Question B, suppose the ends of the ray are rigidly clamped at that temperature 0 degrees Celsius so that expansion is prevented. That is, you do not allow expansion to happen. You have a ray, you fix the first end, you fix the second end. You now supply temperature. Normally, if you do not fix the two ends, the length the ray will increase. The length of the ray will increase. But because you have fixed the two ends, so you don't allow expansion to take place. So the question now is, what is the thermal stress set up in the ray if its temperature is raised to 40 degrees? So this is a technical question, but very simple. Take the Young modulus of the steel to be this, and coefficient of linear expansion to be this. Yeah. The third question, what is the length of the unclamped segment if the temperature drops to minus 40 degrees Celsius? So let's pick the first question. Let me read it again so that you understand. A segment of steel railroad track has a length of that. The original length of that steel is 30 meters, but temperature is 0 at that point. Then when you now increase the temperature to 40 degrees Celsius, the question is, what is its length? What would be its length? What would be its length when you increase the temperature to 40 degrees? So everybody can do that. We just apply this simple relation that I give you, delta L over Li equals alpha delta T. So calculate the change in the length. So delta L is equal to Li multiplied by alpha delta T. And you know the Li is 30 meters. That's why I put that here. Then the coefficient of linear expansion is 11 times 10 to the power minus 6. Then change the temperature. Don't forget, the steel was at 0 degrees Celsius. Then you increase temperature to 40 degrees Celsius. Then change the temperature will be 40. That's 40 minus 0. That's why we have 40 here. You don't need to convert it to, what's it called, to Kelvin. So this 40, when you multiply, you have the change in length to be 0.013 meter. And the question is asking you the length. What would be the length when you increase temperature to 40? That is, you need to add that change the length that you have calculated to the original length. So the final length after you have increased temperature to 40 degrees Celsius is now 30.013 meter. And I believe we understand this. So very simple. It's an elementary question. But let's look at the part B. The part B is saying, suppose the end of the ray are rigidly clamped at 0 degrees Celsius so that the expansion is prevented. What is the thermal stress set up in the ray if temperature is raised to 40? So this one, you just apply this knowledge that when you allow expansion to take place, there will be a kind of a tensile stress. Tensile stress, that is the force over area. The force you apply over area, the cross-sectional area of that material. But in this case, you do not allow expansion to happen. So thermal stress is the same as the tensile stress in the situation in which the ray expands freely. Do we get that logic? You just calculate the tensile stress. So tensile stress you should get when you allow expansion. You see the same thing. Tensile strain, tensile, thermal stress that thing will be feeling. So you are supplying it and you clamp the two ends. So that thing will be feeling a kind of stress. But that stress that thing is feeling, it will be the same as tensile stress if you allow expansion to take place. So that's why I say Young modulus called the tensile stress over tensile strain. So I cross multiply to find my tensile stress, and Young modulus is given the equation to be 20 times 10 to the power 10 Newton per meter square. So let's put it now. Tensile stress is equal to Young modulus. This Young modulus. Tensile, you remember the formula for tensile strain? That's change in length over original length, which we have done before. Then this is Young modulus they give you. This is change in length that you calculated over 30 on 0. That's original length. When you do it very well, you find that tensile stress is equal to 8.7 times 10 to the power 7 Newton per meter square. This is tensile thermal stress that the object will experience since you do not allow expansion to take place. As simple as that. Then the third question is almost like the first question, but in this case, temperature drops. Not that temperature in the first question, they say when the temperature increases to 40, but this one, when the temperature drops to 40, you still calculate change in length as we have done in question A.
Hello, sir. Are you there, sir?
I don't come out to.
Nine network.
Who is the host?
Okay.
Alpha, I won't understand that work now.
Please mute your mic. You are the host now.
What's going on now? Where is the channel? Now network, you go come back. Now network. Okay, thanks. You're welcome.
Please, what's going on?
Na network, na network. I think you don't log and you save out or something like that.
Okay.
I think it's like somebody thinks this one has been posted. How is it happening?
Oh, sorry, student. My network got broken and I was logged out. So how can Adeyemi Uze. Do you have Adeyemi Uze in the on the group? Or let me call about it. Ogujobi Kodija. Yeah, Kodija will be the right person. Kodija. Okay, make me a host. Do you know how to do that? Hello, Ogujobi Kodija. Kodija.
Yes, sir.
You click on my name.
Yes, I've clicked on it.
Make a host, make a code. Just make me. Okay, you see three dots in front of my name. Then click that 3 dots. You see make a host.
Okay. I'm coming.
It is. Okay. Host as top. Okay. Make host.
Yes. Of course.
Did you see it?
Yes, sir.
Okay, yeah, you have done that. I've seen it. Thank you. Oh, sorry,
Okay.
the network logged me out. So, thank you.
Yes, sir.
Khadija is now a co. Okay, let's quickly continue from where we stopped. So I was telling us that question that in the third question they say, what of if the temperature drops to 40? Temperature drops, not increase, to 40 degrees Celsius. You just calculate the change in the length and you subtract it from the original length. So that's what I have for the final length to be when the temperature drops to 40. the final will be 30 minus 0.013, which will be 29.987 meter. And you can see that this length is shorter than or smaller than the original length, which is 30.0 meter. So that is that. Then let's quickly look at this question before we round up the class. Yeah. A poorly designed electronic device has two boats.
So I'm not hearing you. Normal distance. It's when you wear it as standard.
Sorry, the network is seriously misbehaving today. So, and with this time we have, I don't know if we can finish. This question, but let's try our best. If you cannot finish, we'll continue when we resume. You are resuming next week, right?
Yes.
Okay.
Yes, sir.
If you cannot finish this question, we continue when you resume physically. So let me quickly share my this thing and explain. Yeah. So the two bolts are at different electric potentials, and if they touch each other, a short circuit will set in. That's yeah. A short circuit will develop, damaging the device. The initial gap between the end of the two bolts is 5.0 micrometer at 27 degrees Celsius. This is initial temperature, and the gap between the two bolts is this. At what temperature will the bolts touch? Take the coefficient of linear expansion for steel to be 11 times 10 to the minus 6 per degree Celsius, and that of brass to be 19 times 10 to the minus 6 per degree Celsius. Yeah. They say at what temperature will the bolt meet? The initial temperature of the system is 27.0 degrees Celsius, and the gap between the two bolts is 5.0 times 10 to the power minus 6 micrometers, 10 to the power minus 6 meter. So you know when the temperature increases, this bolt will increase, this one also will increase. They are now asking us to calculate the temperature at which two of them will meet each other. Let's change the temperature be delta T. Then this S that you see is for the steel, while B will be for the brass, so that you don't say what's the meaning of this, just to differentiate between steel and brass. So I have delta L equals Li alpha delta T. But this SS is telling us I'm dealing with steel first. Then for brass, it will be delta L equals Li alpha delta T. So this delta T is the same. That is, change in temperature will be the same. The temperature at which, the increase in temperature at which two of them will meet, the two bolts will meet each other. Then when I had change in the length of the steel plus change the length of the brass, it should be equal to the gap between them. That's 5.0 times 10 to the power minus 6 meter. So the formula for this that I've written before is Li alpha delta T plus that of brass must be equal to 5.0 times 10 to the power minus 6. Then I can factorize delta T because delta T will be the same in the two. The increase in temperature will be the same in the two. I factorize it out. So my delta T will now be 5.0 times 10 to the power 6 over what I have inside the bracket. That's why they give you the original length of the brass, and they give you coefficient of linear expansion for the steel and coefficient of linear expansion for the brass. So let's go back to the question. The original length of the steel bolt is 0.010 meter. The original length of the brass bolt is 0.030 meter. You just put it there, and the gap between is 5.0 micrometer that I've told you. So just supply it here. The original length of the steel is 0.01, put it here. Then the coefficient of linear expansion for steel is 11 times 10 to the power minus 6. Then this for the brass plus this plus, don't forget. Li is the original length of the brass bolt times the coefficient of linear expansion. When you do this very well, just do this one side of the bracket, do this one side of the bracket, add them together, and divide the 5.0 times 10 to the power 6 by what you get. Then your delta T, the increase in temperature will be 7.4 degrees Celsius. The temperature at which the bolt will touch is now 27. Don't forget that the initial temperature is 27. Then this is increase in temperature. That's change in temperature. Just add it. You will have 34.4 degrees Celsius. 34.4 degrees Celsius. That's the temperature at which they didn't say what will be the change. They say at what temperature will the two bolts meet. And you know the starting temperature, which is 27. You have to add the change in temperature to it to know the particular temperature that the two bolts will meet. So, and I put another assignment here for you guys to do it. So it's almost the same. I just change some parameters. Instead of starting temperature with 27, I change it to 28.7 degrees Celsius. And the gap between the both is still the same. Then the coefficient of linear expansion of the two are still the same. Then at what temperature will the both touch? So exactly like what I've done, just do the same then. But remember that the starting temperature is different from what I've done. Then determine respectively the change in the length of the steel and the brass at that temperature. You can do that because I've given you the formula for the change in the length of the steel and the change in it. Once you get change in temperature, you can just put it there to get the change in the length for the brass, for the steel. Put it here to get the change in length for the brass. Or another way, once you get one, you can remove it from 5.0 times 10 to the power minus 6 to get the second one. You still get the same way short. So let me stop here and listen to some questions before we leave the class. So any question before I leave the class? Okay, no question. It means we understand, right? Somebody's raising his hand. Oyebamiji, bless. Okay, Adeni Emmanuel. Okay, I'm listening to you.
Good morning, sir.
Good morning.
In that derivation of gamma is equal to 3 alpha,
Okay.
you get to one place, you wrote final volume is equal to LIWIDI into bracket 1 plus 3 alpha delta T plus 3 into bracket alpha delta T square plus alpha
Okay,
delta
is
T.
he here? Is he here? Can you see my screen?
Yes, is here.
Okay.
So I don't understand.
Which one? This one?
No, the next,
Is
the
it
next
this?
screen.
Okay. This place?
No, the next one.
Up or down?
Down.
Yeah.
Yes, this place.
Okay.
So I don't understand. It's gone again.
Oh. Is he here?
Yes.
Okay.
I don't understand
Which
how
one?
this I mean that delta V is equal to V final minus
Yeah,
V initial is equal to
you mean here?
yes.
Okay.
So I
You
don't
know the meaning
understand how
of
this
okay.
I don't understand how this one is removed. And this
Which
minus the LIWIDI.
okay. How is removed? I didn't remove it. I put it there. Okay, let me explain. This is delta V,
Yes,
and you
sir.
know the meaning of delta V is final volume minus initial volume. All right.
Yes, sir.
Oh,
Yes,
if you
sir.
look here, this is my final volume. You know how we arrive at this. I'll just put it there. This is why I have this
Yes.
one minus the initial volume. That's original volume. That's this
Yes.
VI is this. A line is missing here, and I explained that just factorize out LIWIDI. Factorize it out. If you factorize it out, you remember I said that you will have, if I factorize it out, you will have 1 plus 3 alpha delta t plus 3 alpha delta t square plus alpha delta t raised to power 3 minus 1. Minus 1 will be, that's that minus 1 will not cancel this one.
Okay.
You know the 1 is here, so the minus 1 will be here. If you combine them, that will be 0. That's why I just have 3 alpha delta t plus 3 alpha delta t square plus alpha delta t raised to power 3. Do you understand now? And this is
yes,
what
sir.
I factorized out. Okay, any other question? Okay, if there's no question, so enjoy the rest of your day. I will meet.
Sir, I have a question.
Okay.
Sir, back to the coefficient of modulus, Young modulus. The thermal stress, I didn't get this very well.
Okay.
The thermal
I
stress
said,
was
okay. You know the meaning of stress, Abby?
yes, sir. It's because I was logged out by my network.
Okay. Yeah. The question says we have a ray, a steel ray, and we supply it to it. We can calculate change. So in the part B of the question, they now say calculate the thermal stress that thing will be passing through if you clamp, if you fix, maybe use a very strong bolt to fix this end of that rod. The second rod, the second hand too, you fix it with a very strong bolt, so that even though you are increasing the temperature, you do not allow that thing to expand. You know, there'll be a kind of strain that thing will be passing through. There'll be a kind of stress. That stress is what they want you to calculate. But the way we calculate it is use the knowledge of, if you allow expansion, or if I not clamp the two hands, if I allow expansion, I can calculate thermal stress. I can calculate tensile stress. So just calculate tensile stress. Tensile stress is the stress that we undergo. Let me say, we undergo if you allow expansion. But now they say if expansion is not allowed, just calculate tensile stress. Tensile stress will be the same as the thermal stress that thing will be passing through if you fix the two hands. Do you understand that, or I should explain
sir.
again?
Yes, sir. I get it, sir.
You remember Young modulus, by the formula of Young modulus stress. So tensile stress is for when expansion is allowed, but still the same. If I do not allow expansion, it's the same stress. It's like a pain that will be passing through. So it's still the same. That's what you just calculate. That tensile stress, as you use the same, is the same. Okay, I put it here. The thermal stress the same as the tensile stress in the situation expand freely. So
Hello, sir.
Any other question?
Yeah.
So in the absence of any, so let's end the
Sir,
class for today.
will you repeat this topic when we resume? Hello.
You said?
I said, will you repeat this when we resume?
You said? I cannot hear you. Sure. Yeah, I need to repeat it here.
Are you going to repeat this topic when we resume?
Yes.
Yes.
Thank you, sir.
Okay, you're welcome. So let's call it a day.
Bye, sir.
All right, sir.
Bye.
Bye, sir.
Bye.
Bye, sir.
Bye.
When you come, bye, sir.
Bye, sir.
Bye.
Bye, sir.
All right.